quadratic equations. So methods for solving quadratic equations. So, and quadratic equations are just like degree 2 polynomial equations, right? So the highest exponent is 2. So factoring is like the preferred method because, well, not only because it leaves like the least amount of room for error, right? Like people rarely make calculation errors in factoring, but also because it's more versatile. So like we can solve any polynomial equation by factoring as long as the polynomial can be factored, right? So it doesn't have to be quadratic. It can be degree 3, degree 4, degree whatever. As long as we can factor the polynomial, we can solve it by factoring. So this works for any polynomial equation as long as the polynomial can be factored. And then yesterday we talked about the square root property. And when can we use the square root property?
When something squared equals a constant?
Yeah, when the left side is a perfect square, right? Can use when the equation has the form something squared. So either it's a single variable squared or it's something else in parentheses, and then the only thing outside the parentheses is that exponent of 2 equals a constant. So let's say we wanted to solve two x squared minus 5x plus 1 equals 0. Well, first thing I do is try to factor, but my AC is 2, right? And my B is negative 5. The only two things that multiply to 2 are 1 and 2, and there's just no way I'm going to add, no matter what I do with the signs, there's no way I'm going to add 1 and 2 or negative 1 and negative 2 or negative 2 and 1 to get negative 5, right? It's just impossible. And so that can't be factored. And then as far as the square root property goes, well, if I want something squared, the only perfect square in this equation is this x squared right here. And if I moved everything else over to the other side, what's wrong with that?
There's still an x on it.
Yeah, that 5x would be on the right side, which means it wouldn't be a constant, right? So no matter what I do, that 5x gets in the way. Either it gets in the way of the left side being a perfect square, or it gets in the way of the right side being a constant. So there's no way for me to write that as something squared equals c, except through a process called completing the square, which we're not going to get into. If you take pre-calc, you'll do it in pre-calc. But we don't need to do it because somebody already did it for us. So at some point, somebody took... so the solutions to, so somebody took this equation, ax squared plus bx plus c equals 0. So just a general quadratic equation. And they manipulated the equation by completing the square to write it as something squared equals c. And then they solved for x and got a general formula, are given by, and that general formula we call the quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac. It's not really that exciting. Like, the math behind the quadratic formula could derive the quadratic formula just like some dude did at some point before they put it in a textbook. As long as you know how to complete the square, like, it's actually pretty simple. They're pretty simple calculations, which is why it's not like named after some famous mathematician, right? Because like anybody can do it. But it is pretty handy because it prevents us from having to complete the square for individual equations. On our own, we can just instead plug it into the quadratic formula. So this is our last method for solving quadratics. It's called the quadratic formula. And it's handy, but it also has like a lot of drawbacks. Like, we can only use it for quadratic equations. So if I have like an equation like 3x to the third plus 4x minus 5 equals 0. Like, just because that has 3 terms doesn't mean I can use the quadratic formula, right? That's not a quadratic equation. It's a degree 3 polynomial equation, and so the quadratic formula won't give me the solutions to that equation. Like, it has to be a degree 2 polynomial in order for the quadratic formula to work. So it's a handy tool, but don't go overboard with it. People get really excited about it and want to use it for everything, but unfortunately it only works for like a very specific type of equation. So we have to be a little bit careful not to go too crazy. It also leaves a lot of room for error. Like, the calculations that, like, the simplifying that we have to do can get a little bit messy. So factoring really is like always the easiest way to solve equations. But if you can't factor, then this is pretty handy. And we will use it a lot for application problems. So when a decimal approximation is appropriate, then the quadratic formula is really helpful, because if there's decimals involved, we definitely don't want to factor. Yes?
Is there any one method that you could use on everything?
Well, yeah, you can, depends on what you mean by on everything. Like, there is no single method that will solve every single equation in the whole universe. But, like, you can solve any quadratic with the quadratic formula. You can solve any quadratic by completing the square. You cannot solve any quadratic by factoring because it has to be factorable in order to solve. So no, I guess, is the answer. Yeah. There's other formulas for other types of equations. They're just so like, there's a cubic formula that solves degree 3 polynomial equations, but it's so stinking messy that, like, I learned it once, like, when I was an undergrad, and we used it like one time, and then he was like, "This is so stupid." So, like, off we went and didn't ever use it again. Like, there were other ways that are easier to solve, because it's so messy. So the quadratic formula, the reason we even use it is just because it's pretty neat. You know, like, you can derive some formula to solve basically any polynomial equation, but they get so nasty that it's, like, useless. You know, it's, like, not worth knowing, because using it is so messy that you might as well just do something else. So this one is pretty nice and neat. We just have to be careful not to overuse it. So not to use it on equations that aren't quadratic in particular is where mistakes get made. So let's go ahead and do a couple. Let's find the zeros. Oh, I guess I didn't finish solving this one. We'll do this one. So we decided we can't factor it, and so I'm going to say A is equal to 2, B is equal to -5, C is equal to 1. And then the quadratic formula is really just like plug and chug. Like you put the numbers in and then you simplify as much as possible. Make sure that you include the x. So the left side of the equation is just as important as the right side, just like any other equation. So we have x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Whoops, 2. When you do this, I recommend taking this entire thing and putting it in your calculator exactly as written. I was talking with some people in the last class about it. If you find yourself making errors putting that -5 squared in, like if you're forgetting the parentheses or something, remember that 5 squared and -5 squared are the same. So when you do that, you can really just type 5 squared minus 4 times 2 times 1 if you want, to avoid like having to put the parentheses around the negative, because you get the same thing if you square a negative and a positive. So if that helps avoid sign errors, then that's fine. I would just type the whole thing in. Don't like try to do it piece by piece, because that middle bit is where sign errors happen the most. Like if A or C is negative, then we have like 2 negatives or 3 negatives, and it can get a little hairy. But if you type the whole thing in at once, it'll just take care of all of it for you. So what do we end up with under that radical? What is it? 17, okay. Over 4. And that's as far as we can go here. So one of the nice things about the quadratic formula is that when you're simplifying this expression, if you can't simplify the radical, so if you can't pull any factors out as coefficients in front of the radical, there is no hope of doing any other simplifying. Like you won't be able to cancel anything. The only way you'll ever be able to like cancel anything is if you can pull something out of that radical. So 17 is prime, which means we can't factor it, which means we can't simplify the radical, which means we're done. There's not any chance of doing any other simplifying if we can't simplify that radical. Whoops. Did everybody get 17 when they put that in their calculator? I want to make sure we're all plugging it in right. Okay. Let's do another one. So let's find the zeros of f of x equals 3x squared minus 4x plus 2. Okay, you guys try that one. Oh, that's a good one. So we have x equals 4 plus or minus the square root of -4 squared minus 4 times 3 times 2 over 2 times 3. And we get x equals plus or minus the square root, what was it, -8? Over 6. This is not a real number. So the definition of an imaginary number is that it contains the square root of a negative. And so because we're only concerned with real solutions in this class, we're just going to say no real solution, or no real zeros. And the reason we care only about real solutions is that like our main focus in this class is the relationship between like symbolic representations and graphical representations of functions, right? And so imaginary numbers don't show up on the graphs of functions. Like the XY coordinate plane is made of like 2 real number lines, right? X-axis, Y-axis. And so imaginary numbers don't show up on the graph, and so they're not going to help us see what the graph looks like or how the graph behaves. But knowing that there's no real zeros, that tells us something, right? It tells us that it doesn't ever go through the x-axis. Oh, I forgot to mention, you guys have to memorize this. There's a song. Well, there's apparently a new song. I wish Katie would come. Katie knows what it is. There's like there's the old like Pop Goes the Weasel one, but then I guess there's like a new one that's like an Adele song or something. Like it's all like modern, and I guess it's very moving. The YouTube video. But I always just I think the easiest way to memorize something is to just use it so much that you memorize it. So if you, every time you use the quadratic formula, if you write it like that before you start plugging numbers in, then you'll just end up writing it so many times that like it'll become automatic, right? So like if you just like take the time to write the formula with the like exactly like that without any numbers before you plug the numbers in, then that can help you memorize it. Or you can put it in your shower or on the My chemistry teacher, my senior year of high school, she sent us all a laminated copy of the periodic table over the summer so that we could shower with it. Literally, she told us we should put it on our shower wall so we could read it while we were showering and memorize it. I mean, it worked. Or like put it on like the dashboard of your car. Like I always I put things on the dashboard of my car, and then every time I stop at a stoplight, I read it out loud to myself. Because I mean, if you drive a lot, that works. If you don't drive that much, not very helpful. But there's lots of different ways to memorize, but whatever works best for you. I am not a fan of the song because I always get the song stuck in my head, and then like I cannot get it out for like months and months and months. It drives me nuts. But I guess that's the point of the song. Okay, so let's do this guy. Let's find the x-intercepts. Of the graph. Of f of x equals, what am I? A third minus 4x squared minus 9x equals 0. Oh, not equals 0, sorry. It's not there yet. Okay, what should I do first?
Factor an x.
Before I factor out an x? I set it equals 0. I like what you guys are thinking. We will factor out an x, but first we're going to set it equal to 0. And like this is one of those steps that's important because like this week all we've done is set things equal to 0, so it seems like, oh well, I don't need to do that because I know I'm setting everything equal to 0. Next week we will be finding other points on the graphs of quadratic functions, so it'll be important that we can differentiate between when we're finding the x-intercepts, when we're finding the vertex, when we're finding other points. So you want to make sure to write this step so that you don't get confused about where on the graph you are when you actually find your solution. So yeah, so we have x times x squared minus 4x minus 9 equals 0. And then we can't factor any further than that, right? Because there's no numbers that multiply to negative 9 and add to negative 4. So at this point, we're still factoring, or we're still solving by factoring. So I need to set each of my factors equal to 0. And that gives me one solution, which I want to make sure I don't forget later on. But then that other equation, since I can't factor it, now I'll use the quadratic formula to solve that because it's quadratic, right? So I couldn't use the quadratic formula from the beginning because the original equation is a cubic, so is a degree 3 equation. So I had to do that factoring and splitting that up in order to get a quadratic equation to solve. So we have x equals 4 plus or minus the square root of negative 4 squared minus 4 times 1 times negative 9 over 2 times 1. What'd you guys get under the radical? 32? 52.
I got
Okay, okay, good. And so now I want to simplify. So I'm going to factor that 52. So 4 plus or minus the square root of 2 squared times 13 over 2. So we have 4 plus or minus 2 times the square root of 13 over 2. And so now that I have factored something out of that radical, we can think about simplifying the fraction. We can cancel these. This does not work. We have to, right, because that 4 is being added / subtracted, not multiplied. So we need to factor a GCF out of the numerator in order to factor, or in order to cancel anything. So the GCF here, if I look at these two coefficients, they have a GCF of 2. So I have x equals 2 times 2 plus or minus the square root of 13. Remember, the square root of 13 is just a symbol like x, right? So we're basically factoring the GCF out, just like we would if it was like 4 plus 2x. Over 2. Then those 2's will cancel. And we get x equals 2 plus or minus the square root of 13. And we're almost done, but we were asked for x-intercepts, so we need to give ordered pairs. So my x-intercepts are 0, 0, right? That's from my very first solution. And then 2 plus root 13, 0, and 2 minus root 13, 0. Any questions on this stuff? Okay, so let's look at the discriminant. So the discriminant of f of x equals ax squared plus bx plus c is given by, we'll call it d, equals b squared minus 4ac. So you probably recognize this as, so in the quadratic formula, the discriminant shows up under the radical. And because of its placement in the formula that gives us the solutions to an equation, it actually tells us a lot of things about the function or the equation itself. So the first thing we can find from the discriminant is how many x-intercepts the graph has. So if our discriminant is positive, then the graph of f well, if we set our function equal to 0, then the quadratic formula will give us the x-coordinates of the x-intercepts, right? So if you have a positive number under the radical, how many different solutions will that equation give you, or that formula give you? 2, right? You get one by adding and one by subtracting. So the graph of f has two x-intercepts. So it looks like this or this. So it might open up, it might open down, but it goes through the x-axis twice at two different points. If if my discriminant is equal to 0, so if over here, instead of a positive, if I have a 0 right here, how many different solutions will that give me?
One.
Yeah, just one, right? Because negative b plus 0 is negative b, and negative b minus 0 is also negative b. And so the plus and the minus give me the same solution. And so we're only going to get one solution, so the graph of f has one x-intercept. So that's like when the graph kind of like bounces off the x-axis. So it doesn't actually pass through it, it just touches it once and then goes back in the direction it came. And then the last possibility is if my discriminant is negative. So if I had a negative number under this radical, we kind of saw this already once today, right? What does that mean? Yeah, there's no real solutions, which means that the graph is not going to have any x-intercepts. So the graph of f has no x-intercepts. So that would be like if the whole parabola was above the x-axis, or the whole parabola was below the x-axis. It's an ugly parabola. So it never touches the x-axis or passes through it. So we don't actually have to find the solutions in order to figure out how many x-intercepts we're going to have. We just have to find the discriminant. So let's do one example of this. So find the discriminant. And the number of x-intercepts. So f of x equals, we'll do 4x squared plus 12x plus 9. So go ahead and find your discriminant. What did you guys get? What?
One solution. There's one solution.
There's one solution, yeah. So what was our what was our discriminant? 0, yeah. So b squared minus 4ac was 12 squared minus 4 times 4 times 9, which was 0. And so we have one x-intercept. So that's basically your entire online homework. There's like 5 questions, and just do that over and over again. It's pretty exciting. But the discriminant actually tells us one other thing, which I find way more handy than the number of x-intercepts. It tells us, so if the discriminant is a perfect square, anybody know this one? It's amazing to me they don't teach this in high school. It's like the coolest thing in the whole wide world. I mean, maybe not in the whole one. Yes, you see, somebody learned it. So if the discriminant is a perfect square, then ax squared plus bx plus c is factorable. So if we put all of this together, it's pretty convenient, right? We know that factoring is like the preferred method to solve, but if I have an equation with kind of large numbers in it, so if I want to solve like 12x squared minus 2x minus 15 equals 0. So if I want to know if that's factorable, I have to multiply 12 and negative 15, and then make a list of all numbers that multiply to whatever that number is, and then add them all together and see if any of them add up to 2, right? Which is somewhat tedious, especially if you don't even know if it's going to work in the end, right? Like, it's worth it if you know it'll work, but if you do all that work and then you find out it can't be factored, it's kind of a pain, right? So instead, we can say b squared minus 4ac, so our discriminant is equal to negative 2 squared minus 4 times 12 times negative 15, which is equal to what?
720.
What is it?
720.
720. Everybody else get 720? Last time I took one person's word and it was wrong. My last time. So 720, is that a perfect square? Well, how can we tell if that's a perfect square? Yeah, you just take the square root on your calculator, and if you get like a decimal, or if you have a calculator that simplifies square roots, if you get something that's still a square root, then it's not a perfect square. And if you get a whole number, then it is a perfect square. Is that a perfect square?
No.
So this is not a perfect square. And what that means is that I'm not even going to bother trying to solve this by factoring, because this polynomial is prime. So it also gives me what's under the radical in the quadratic formula. So not only have I decided I'm going to use the quadratic formula, but it's like halfway done for me already. So x equals positive 2 plus or minus the square root. Well, I already know that b squared minus 4ac is 720 over 2 times 12. So now we just have to simplify. So x equals 2 plus or minus, oh gosh, 36 times 12 times, thank you. So this is 12 squared times 5. So we get 2 plus or minus 12 root 5. I did not really want to do that. And then we can factor out what on the top?
2.
Yeah, 2. So we get x equals 2 times 1 plus or minus 6 root 5 over 24. Oops. gives me 12 down here. So x equals 1 plus or minus 6 root 5 over 12. And then we're done. So one other nice thing about knowing if a polynomial is factorable or not is that it also helps you figure out what type of solutions the equation has. So if the polynomial is factorable, then the solutions are rational. Remember we talked about rational and irrational numbers when we were talking about radicals, right? So square roots, like radicals, are all irrational if they're not the square root of a perfect square. So if a polynomial is factorable, then the solutions to the equation are going to be like fractions or integers, right? If it's not factorable, then your solution is always going to contain a square root. And so that's kind of a nice thing to know as far as graphing, because graphing rational numbers is way easier than graphing like irrational numbers. So if I was graphing a polynomial and I knew the solutions or the x-intercepts were not rational, I'd probably like think of other points to use, or choose to use other points to graph my polynomial, because it's kind of a pain to graph irrational numbers. You can't do it exactly, right? You have to kind of estimate. So there's all sorts of interesting things that we can learn just from the discriminant. Like I said, on your homework tonight, you will basically be doing just that. But it gives us other information as well that can help us as we move forward and start graphing these things and finding other characteristics. You're not done yet. Don't you want to solve one more equation and try this all out on your own? Yeah, I see Peyton wants to. Okay, so solve 10x squared minus 8x minus 9 equals 0. $424. If you find yourself making mistakes with the signs on that, like the most common mistake is to forget the parentheses around the -8 when you square it. You can avoid that just by dropping the negative. Like 8 squared is the same as -8 squared. So if you just do 8 squared minus 4 times 10 times -9, then you don't have to worry about the parentheses. So then that was not a perfect square, and so we have to use the quadratic formula. Did anybody simplify the square root of 424? 106. So we have 8 plus or minus 2 times the square root of 106 over 20. And we can factor out a 2 in the numerator. So we get 4 plus or minus 2 root 106. Oh, there's no 2 there. Root 106 over 20. So that cancels, and over 10. Resist the urge to cancel more, right? Once we factor, like the only potential canceling that you can do in these problems is if you can factor a number out of the entire numerator. So once you've done that, don't then be like, oh, I can cancel the 4 and the 10, right? Like, once you get rid of that GCF, like, there's just no more canceling that you can do. Okay, guys,